computer would be more and more confused as it tries to reassemble my sound. Eventually, it will become robotic and alien.
Until now, we've been talking about sound that happens out in the world, and we've been looking at spectrograms of those sounds. Today, we're going to spend time talking about how we get the two to go together and pull back apart. In other words, we're going to be talking about recording and digital audio and analog audio as well. So we're going to be talking a little bit just about how microphones work and how we get sound into a computer. Through the process of sampling, we turned it into a digital file and then convert it back into analog for our ears. Here we go. Now we're going to be returning to the recording of a hummingbird from 2 lessons ago. And this time we're going to be thinking about how we can capture the sound of the hummingbird's wings with a microphone, and then how we can play that sound back with a speaker or headphones. When we have a recording, we make that with a microphone, and microphones come in a lot of different sizes and shapes and designs, but they all work the same way. What they're doing is measuring the sound, the differential of airwave pressure, and measuring that in voltage differences. So we talked about the hummingbird being next to our ear, and our ear is the receiver. In this case, the microphone would be the receiver when we record the hummingbird. So just like our ear, the microphone has what's called a diaphragm in it. Usually it involves magnets. And this is, like our eardrum, is a sympathetic entity that can react to the waves around it. So inside of our eardrum, there is material that moves as the air around our ear moves. Same thing with a microphone. The diaphragm moves when the hummingbird is next to it. The hummingbird flaps its wings toward it, and the microphone moves in. It flaps its wings away, and the microphone diaphragm moves out. And so it obviously records. It records the differences and how far it moves, which would equate volume, and of course in time. And a microphone is an analog piece of equipment, meaning it's not digital information yet, it's analog information, and that sends out an analog signal. So an analog signal is the type that runs through an audio cable, like a XLR mic cable or a guitar cable. That's analog audio information. It's fluctuating voltage, so it's taking the sound, in the case of a microphone, and converting what it receives into a fluctuating voltage signal. So we can think about microphones like our ears. They pick up sound and translate a message. Now we're going to stay talking about analog audio and jump to the other side, the speaker, which is kind of like our voice, where it obviously projects the sound back at us. In between there, audio could stay analog or it could be converted to digital. And in just a bit here, we're going to be talking about digital audio. But for now, let's just talk about speakers themselves and how they work. Both microphones and speakers could be considered transducers. It's a term that you'll hear in this topic because that basically just means converting something into something else. So the microphone is converting the actual air pressure differences into a fluctuating voltage signal. And similarly, the speaker will be converting the fluctuating voltage signal into movement of the speaker cone, which will push airwaves and thus bring us full circle. The speaker, it takes the analog signal and reproduces the sound by moving in and out. So I've talked about how the speaker cones will move in and out, just like the wings of the hummingbird. They move and trace along the path given to them by the analog signal, and they recreate sound that way. digital signal is not fluctuating voltage. It's like all digital info. It's numbers. Data for a sound is calculated in samples. So the way that that works is as the analog signal is fed into an ADC, which is an analog to digital converter, then it converts it into digital by sampling it. Now this use of the word sample is different than when we talk about sampling in music recording, when you take a little bit of someone else's song and sample it. And that is a different meaning, although they are kind of alluding to the same meaning of the word sample, which is to take a little bit of something. In this case, the little bit that's being taken for a digital audio signal it's a measurement of the volume in time. So let me jump over and show you how samples work in the waveform. Waveform for our hummingbird. We can now use it to think about sampling. So if we had an analog version of this sound that we were looking at, this is what it would look like, coming through the microphone, going into a speaker. But this is very subtly different. This is a digital signal, and I will show you why. When I zoom very far in, now we're getting down to the thousandths of a second, we can look at the sound, and again, this would look like analog would look. But if I go even further in, and I look very, very closely, we can see these dots. These dots are the samples. So an analog signal would not have dots because it wouldn't need them, and it would follow probably about the same trajectory, but it wouldn't have these sample points. The way these sample points work is when an analog signal is fed into an ADC, an analog to digital converter, what it does is to sample the volume or amplitude. So if we think about our labels over here in decibels, we can see what it's doing. So at a regular pace, you notice the dots are the same distance apart. I'm zoomed very, very, very far in now to the 10,000th of a second. They're all the same distance apart. What it's doing is saying, how loud are you now? 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 And it takes a reading of the volume level at that point. So here it says -30, and that is encoded as a single binary bit of data that says -30. The next dot down is -32. All the way over here we have -18. And so it's a reading of the volume as we go along in time. What it then does when we have our DAC, our digital to analog converter, is the DAC converts it back to analog by connecting the dots. So when I press play, I hear through the speakers, through the transducers, an analog sound. I hear an acoustic sound that is the computer tracing, connecting the dots between these samples. So essentially, an analog signal would look like this without the dots, and the digital signal has the dots that are being connected. The idea of digital audio has been around for a long time, but in the early days, it faced a problem of computing power and speed such that we couldn't necessarily represent all of the frequencies in music perfectly or in any audio signal. And that's because we need at least 2 samples for every oscillation of a waveform to capture it. So that means that if we want to capture the highest note we can possibly hear, which we learned before is 20,000 hertz, then we need at least twice that many samples. That means 40,000 hertz for a sample rate. In other words, we need dots to happen 40,000 times per second. And that was a lot to ask for early computers and gear. But now, our computers are well up to speed, and in fact, CD quality is of course 44.1 kilohertz sample rate, meaning it can technically reproduce a frequency of 22,000 above what we can hear. And sample rates go beyond that to 48,000, 96, and even 192 kilohertz. So we can safely and quickly represent all of the pitches we could possibly hear in digital audio now. So if you think about an A440 or this hummingbird that was about 100 hertz, so the hummingbird wing flaps 100 times per second. So in order to capture that 100 times per second, we need to be sampling it at least 100 times per second. In fact, to really get the sound right, we need to sample it way more than that. So if there were less dots, they would not connect. So just for fun, I want to play around with what's called a downsampler, where we can use modern tools to actually go back in time to the lower sample rates where the sound would not be reproduced perfectly. And so as we crank down the sample rate for the sound, we'll hear what it would sound like if we didn't have enough samples to reproduce the sound. Now what about if I had less samples? So if I go from my current samples down to 4 times less samples, then we would have less points of data to recreate the sound that I'm making. And thus, the computer would be more and more confused
as it tries to reassemble my sound. Eventually, it will become robotic and alien.
Alright, that wraps up today's lesson. Next time we're going to be getting into types of sounds like speech sounds and how we get a sense of pitch from a sound through periodicity. I'll see you there.